Hello, welcome to lesson 12 of my Waves and Wave Phenomena playlist. This lesson we're learning about resolvents of diffraction gratings. So basically putting together the last two lessons that we just covered. You have two images in this screen. This is an image we saw with a diffraction grating, 100 lines per millimeter to be accurate. And the one on the left is a less resolved version of the same image. So how do we define resolvents of diffraction gratings? How can we determine what wavelengths can be resolved with diffraction gratings? Now on the screen, I have drawn a big single slit and representing a diffraction grating in front of it. It's been divided into sections of 1 centimeter each. So D between two consecutive slits is 1 centimeter. There's a beam of wavelength lambda, which has a thickness of 3 centimeters, illuminating this diffraction grating. Now, depending on how many lines per millimeter there is on the diffraction grating, D will be different. In my diagram, D is 1 centimeter. In a diffraction grating, this will obviously be much smaller, but these are numbers to help our eyes and to have a bit of a scale diagram. So D is 1 centimeter and I have a beam of thickness 3 centimeters. Now in this case, how many slits is this going to be illuminating? 3 obviously, because I have a beam width of 3 and each slit is 1 centimeter, so I have a light beam passing through 3 slits. Now on the screen, these 3 slits will show the behavior of multiple slits we learned the previous lesson. So it will have an intensity pattern as such. Central maximum, which has highest intensity, and first max, and the second max, and a symmetric pattern on the other side. What happens if I increase the width of this beam? If I replace this 3 centimeter beam without changing anything with a 9 centimeter beam, in that case, how many slits will the beam be passing through? The answer is obviously 9. 9 centimeter beam illuminating slits of width 1 centimeter. This is now 9 slits instead of 3. So behaving as 9 multiple slits rather than 3, we see the behavior that we saw earlier when we discussed multiple slits. The fringes stayed at the same locations, but they got narrower and sharper. Let's go back to the previous screen and compare with the next one. Okay, let's explain what's going on. I have a beam of wavelength lambda, and I'm going to define a resolvance factor R of my diffraction grating. Now, I still have 9 slits in this case, so N, capital N, is going to be the number of individual slits illuminated by the beam of light. M would stand for the order of diffraction, so the center would be M equals 0. The first maximum would be M equals 1. This was N before, but now that we have capital N for the number of slits illuminated, to avoid confusion, this is capital N and this is represented with the letter M. And delta lambda stands for the smallest difference in wavelength that can be resolved. Now, what we mean by this is we can have a wavelength of 650 nanometers. But in the first order diffraction maximum, we might be able to clearly see the maxima within a certain range of wavelengths. Bigger than that range, the central max of the two distinct wavelengths will be closer to each other than the condition of the Rayleigh criterion, so they won't be resolved. So what are the conditions that allow us to resolve a certain range of wavelengths? Now, this is a formula that is given in the formula booklet. R stands for resolvance factor, N is, as I just described, number of slits illuminated. M is the order of the maxima. Lambda is the average wavelength that is used, and delta lambda is the smallest difference that can be resolved. This is a cleaner summary of what I just explained, so use it for your notes. And here are some solved examples. This is from our Oxford textbook. Two lines in the emission spectrum of sodium have wavelengths as given. Calculate the number of lines per millimeter needed in a diffraction grating if the lines are to be resolved in the second order spectrum with a beam of width 0.1 millimeter. So, as confusing as all this may sound, this is very straightforward. You can use the average or either of these wavelengths as your lambda. The difference between the wavelengths to be resolved is 0.6. When you calculate that ratio, you have your resolvance factor. We're looking at the second order spectrum, so M is 2. This substitution gives you N, so we have a beam that passes through that many lines. These lines are within 0.1 millimeter, that's our beam. So using that information, we find that our diffraction grating should have around 5,000 lines per millimeter. Here's another example from the textbook, end of chapter questions of topic 9. Explain what is meant by the term resolvance with regards to a diffraction grating. That's a definition you can give as such. And then you have a numerical calculation. You have the resolvance factor to be 2000, so this is R. And we have the incident beam, which has a width of 0.2 millimeters. For the first order maximum, that means we're going to use M equals 1. How many lines per millimeter must the grating have? This is very similar to the question we just looked at. R is given, M equals 1, beam width of 0.2 millimeters. Based on what we know, we have R to be 2000. Dividing it by 1 gives N as 2000 lines illuminated within the beam width, which is 0.2 millimeters. So if we have 2000 lines in 0.2 millimeters, there would be 10,000 lines per millimeter. So this would be the label on our diffraction grating. The second part gives us hydrogen lines wavelengths as such and asks if our diffraction grating will be able to resolve these lines. Now, to decide whether our diffraction grating is going to be able to resolve these wavelengths, we have to find lambda over delta lambda ratio, which is also R for the condition we're given. It gives 3281. That's the required power to resolve these wavelengths. But our diffraction grating doesn't have that power. Therefore, our answer is no. These lines will not be resolved with this diffraction grating. Now, I will show a couple of homework questions for you, and you'll find the solutions on my next video.